let's go and get started. We actually finished our lab just here a little bit ago, so we're getting a little bit of a lot of a late start. So it'll be a much shorter lesson than usual today. Hopefully it was beneficial to actually see what we've been talking about, the cases of image formation, not just see them in the textbook with ray diagrams, but actually see how as the lens position moves or as the object moves in relation to the lens, the image forms at a different location, different size, things like that. We got a chance to see where when the object is placed virtually at the focal point, you don't get anything formed at all. We got a chance to see how when it comes in closer, you get that virtual image. We also got to see with an infinite distance away that bright spot at the focal point, and a little ignition from there. So anyway, hopefully really, really helpful to see that. We also saw how the diverging lens does not allow the light to just go through, it's pushed outward from it. So we got to see the difference between the converging and the diverging lens. We'd seen it with lasers earlier, seeing it now with the sun and other things as well. So hopefully that was helpful. With then all of this, one of the most practical uses of lenses, I say one of the most because there are several, we just discussed an LCD projector in the other room, but one of the most practical uses is of course for people like me who have bad eyes, and actually making lenses to help to correct bad eyesight. And so on page 304 we have the Lensmaker equation. I want you to go ahead and put that in your notes. It's the next equation for you to know, the Lensmaker equation. And remember we said that the focal length of a lens isn't determined by the radius of curvature, but rather by both radii of curvature. Now, of course, we saw with our lenses, they all had the same curvature on both sides. So it was nice and symmetric, everything was beautiful, but most lenses are not to say all lenses have to be that way. So there's two radii of curvature in question, and of course the index of refraction matters. What the lens is made out of matters as well. So the Lensmaker equation accounts for all of that. It's that the reciprocal of the focal length is equal to the refractive index minus 1 times the difference of the reciprocals of the radii. 1 over f equals the quantity n minus 1 times the quantity 1 over r1 minus 1 over r2. Now a couple of things to point out. Obviously, f represents the focal length. A positive focal length indicates a converging lens. It indicates that the light can indeed actually converge. A negative focal length indicates that theoretically the light converges on the same side of the lens, meaning it doesn't actually go through and converge. So a negative indicates a diverging lens. A negative focal length indicates a diverging lens. The n, of course, is the index of refraction. That makes a difference. But notice the minus 1. Remember all the indices of refraction except for a diamond started with 1 point something? Basically, you're taking the 1 off and you're just being left with the point something, unless, of course, we have a lens made out of diamond, which would be highly improbable. Let's be honest. I mean, what would you grind it with? You know, I mean, you think about it, you have to grind it and smooth it and make it and shape it. How are you going to do that? I don't know. They have methods, obviously, of cutting diamonds. I don't know that shaping the diamond is the easiest thing in the world to do. Nobody would afford it anyway. So practically speaking, this will always be a decimal value. The R1 and the R2, remember there are two radii of curvature. The R1 is the radius of curvature for the side of the lens closest to the object. For the side of the lens closest to the object. Now, for illustrative purposes, let me put it this way. You've seen my lenses, kind of the cross-section of them. You've seen how at the front side of the lens, if you look at the glasses, there's a little bit of just the tiniest bit of an outward bulge. It's not perfectly flat at the front of my glasses, a little bit of curve. But then you notice it's much thicker on the edges, and it's thicker on the edges so that they can curve the inside of the lens more. So by curving one side in and then slightly bowing the other side out, it produces something that looks as good as glasses can look, for shall we say, but it still bends the light the way that we want. Well, this is Kendall, and this is Audrey. Michael is not with us at the moment. We hope you get better, Michael. But this is Kendall and Audrey. These are the objects in question. You are objects now. I've objectified you. Sorry. All right, so these are the objects in question. This surface surface is closer to you. As I stand here looking at you, this side is closer to you, so this would be surface 1. This is closer to my eye, this surface is surface 2. What we'll have to do to determine radii of curvature is imagine if this curve kept going. Now it's very slight, but if it kept going, you get the idea, we get a circle around here, correct? So the radius of curvature would be something like this. That would be radius 1. This surface, it's a little easier to picture the circle finishing something like this. Its radius might be something like this, radius 2. You can see that radius 1 is considerably larger than radius 2. And that's the way the glasses are designed to be for most people, because most people like me are nearsighted. There are some farsighted people. We'll talk about that a little bit later on, how all that works. But we've got these two radii of curvature. So R1 is the radius of the side closest to the object. That implies then that R2 is the radius of the side further. I don't know that we need to write that down. That should be relatively easily deduced from that. What we do need to understand is this, the sign convention for the radii. Radii are positive when they are away from the objects. You notice both of these radii go away from you. Therefore, both radii are positive radii for my glasses. If the radii go away from the object, or if a radius, I should say, goes away from an object, it's positive. If it goes toward the object, it's negative. Another way to think of this, by away from the object, could mean this, through the lens. The light from you, ladies, goes through the lens to where the radius is. Since the light went through the lens to where the radii were, it's positive, because anything through a lens is positive. That's what we would expect light to do. If, however, the radii were toward you, for instance, I turn the glasses around. For one thing, it's very distorted, because it wasn't made to be worn this way. But if I turn around, you're still clear. I can still clearly see you. It's just blurry around the edges, and it gives me a bit of a headache. But anyway, if I were to turn it around, well, Kendall, Audrey. Got a big head. Just kidding. Just in the drawing. Just in the drawing. Okay. Well, now this is no longer surface 2. This is surface 1. This is surface 2. Which means that this radius becomes radius 1 and this radius becomes radius 2. But now, because both radii are toward you, both radii become negative. Do we see how that works? And really, truly, the math will work out the same regardless of how the lens is tilted. We just have to account for it accordingly. Look, if you would, in your textbooks. There are 4 different pictures shown in your textbooks for how the signs work. Notice the object in question is a little bishop chess piece. The first lens that you see is kind of like my glasses. The one side, surface 1, which has the longer radius 1, is away from the object. Notice the shorter radius, the more curved side. By the way, that does make sense, doesn't it? The bigger the radius, the less curvy. The smaller the radius, the more pronounced the curve, right? When we open the compass just a little bit, make a little arc, it's really curved. Open a lot, make a little arc, it's barely curved, okay? So longer radii are flatter surfaces, so to speak. All right, both radius 1 and radius 2 would be considered positive in picture A. Now in picture B, this one's kind of unusual. Radius 1 is still positive. What about radius 2? It's flat. It's infinitely large. Does that make sense? If you had an infinite radius, it would be flat, theoretically. What would be, though, the reciprocal of infinite? 0. The reciprocal of infinite would be 0. So we would just ignore that radius 2 in that instance. For those who are watching on YouTube, that video that you watched, kind of showing what we did with the lasers here in the classroom that didn't show up very well, they used a couple of lenses that did have flat surfaces on them, planar surfaces. Look at picture C. That's that diverging lens, that double concave lens. Do you notice that surface 1, radius 1, would be a negative radius, whereas radius 2 would be a positive radius? We see that? And then looking at example D, both radii are kind of like what I showed in this example. Both radii go toward the object, so both radii would be negative. Does that make sense? Consider this for a moment. Let's suppose we took the lenses that we've been using quite a bit for our demonstrations the last couple of days. Right? We took those squatty lenses. So we took a lens something like this. Well, let's put the object, let's say, Kendall, do you want to go on the right or the left? Or left or the right?
Left.
You want to go on the left. So this is Kendall. That means that this surface here is surface 1, this surface is surface 2. Now picture it in your mind. If you were to complete surface 1 as a full circle, where would the circle go? Point. If you finished surface 1's circle, class, where would it go? That way, wouldn't it? Take surface 1 and just continue that circle around. So surface 1's radius must go like this. That's radius 1. Would radius 1 be positive or negative? It would be a positive radius because it's away from the object, or Kendall. If we were to take surface 2 and finish the circle, where would surface 2's circle form? Over this way now, wouldn't it? It looks like it'd be a little bit bigger because surface 2 is a little bit flatter, but it would come somewhere over here. So its radius, which would be a little bit longer, radius 2, would be a negative value. Does that make sense? Or consider if we had a somewhat flat surface here, and a more pronounced curved surface here, and suppose we had, Audrey, do you want to be on the right or the left?
Right.
You want to be on the right side. Audrey. All right. All right, so which one is surface 1, which one's surface 2?
The one on the right is surface 1.
This one, the curvy one is surface 1, the flatter one is surface 2. Now surface 2, because it's flatter, is going to have a longer radius. Surface 1 is more rounded, it's going to have a shorter radius. This will be radius 1, this will be radius 2. What will be true of both radius 1 and radius 2, class? Both positive because they're away from the object. Does that make sense how the signs work? That's very important. Now let's look at the example problem and try to put it all into practice and actually put it into the equation. Read example 20.6 for us if you would, Kendall.
One has a convex surface and a concave surface with radii of magnitudes 15 centimeters and 25 centimeters respectively. The refractive index is 1.52. If the convex side is toward the object, A, what is the lens's focal length, and B, what is the lens converging or diverging?
All right, here's how I will recommend you draw it. I would recommend starting by drawing your focal plane. I would start by lightly drawing. I usually use a light dotted line. I would lightly draw the focal plane. The first side, it says, class, is convex. The convex surface, is it going to cave in toward the focal plane, or is it going to bulge away from the focal plane?
Away.
It's going to bulge away. Now, its radius of curvature is 15 centimeters. Is that the bigger number or smaller number? Smaller number means more curved, right? So whatever curve you decide to give, you bulge outward away from the focal plane with a certain amount of curvature. The next surface is going to be a little bit flatter than this one. Does that make sense? And the next surface, it says, is a concave surface. Now here's the problem. I can't start at the focal plane and cave in toward it. So we're actually going to have to come out just a little bit. It's not going to be very curved. We're going to come out just a little bit from the focal plane to give myself room to do just a little caving in toward it. Do we see that? The sketch is going to be helpful if you draw it somewhat accurately. Now, not life or death on the accuracy of your sketch, but it'll help if you draw it somewhat realistically. So we have our convex side bulging out. We have our concave side caving in. The concave side is more flat. It's less caved than the convex side is bulged. Now, it says that the convex side is toward the object. This is the convex side. The object goes here. You could draw a tree, person, or write OBJ, which does not mean Odell Beckham Jr., who is still unemployed. All right. Anyway, because he wants too much money for a guy who's always hurt. Kind of like Lamar Jackson. As a Colts fan, I don't want Lamar Jackson. Too expensive, giving up first-round draft picks, and he's always hurt. And he's a bit of a diva. I don't want the diva. Anyway, I digress. All right, this is not a Colts podcast. This is a physics class. So let's get back to physics. I want to go ahead and draw the radii. Now notice, this curve puts the radius on which side, the left or the right? Picture the circle finishing. It's going to go over here on the right. That radius is 15 centimeters. The next surface, again, I know there's not much curve here, It's a little bit caved in. If you finish the circle, is it going to go to the left or to the right? Also to the right. Now this one's longer because it's flatter. This radius is 25 centimeters. Since the object is over here, the convex surface's radius is radius 1. It's the radius of the first surface. This is the second surface, this is the second radius. And both radii are positive because they're both away from the object. The last bit of information they tell us is this lens is made out of some kind of glass that has a refractive index of 1.52. Now again, normally because you won't be talking through the picture, it won't take nearly that long to draw the picture, but wanted to talk through so we understood how to put it together. Once you've got this, we go to our Lensmaker equation to find the focal length. We'll say that 1 over f is equal to, now let me tell you what we're not going to do. What we're not going to do is write 1.52 minus 1. We're not going to do that. Instead, our brain is just going to knock the 1 off, so instead my n minus 1 becomes, that's what we are going to do. All right, so we're going to knock the 1 off and just write 0.52. And then in the parentheses, and I do recommend you take the time to show this, reciprocal R1 minus, don't lose that, reciprocal R2. Now, if radius 2 is negative, what could you do with the minus and the negative? You could cancel to make a positive, and I'm okay with that, but I want you to show writing that out. From here, we'll start with the reciprocals, and we got pretty good with reciprocals earlier from the mirror equation. So reciprocal 15 minus reciprocal 25 equals. Solve that parentheses first. You should have a little bitty decimal, 0.0266, blah, 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 blah. All right, now we're going to take that and multiply it by the 0.52. And finally, what you have on your calculator is the reciprocal of the focal length. We want the focal length. One more time we hit the reciprocal key, and that gives us the reciprocal of the focal, or that gives us the focal length to be
72.1.
Okay, rounded off. I believe we have 2 sig figs everywhere. Yes, so we'll say the focal length is 72. Now, what unit? It depends on the units used for the radii. The radii use centimeters. My answer uses centimeters. If for some reason it was millimeters, we would do millimeters. If it was inches, we would do inches. If it was meters, we would do meters. That would be a really big lens. So 72 centimeters is our focal length. Letter B asks the question, is the lens converging or diverging? Well, for that, we look at the focal length's sign, S-I-G-N, not S-I-N-E, and the focal length comes out positive, which means, class, this is a converging lens. Questions on that? Parts A and B. Part C, they say now turn it around so that the object is on the concave side. Now I'm lazy. Rather than turn the lens around, I'm just going to write OBJ over here. Now that does a couple of things though, that changes some things. First of all, both radii just became negative. This becomes negative 15 and negative 25. Something else changed as well. Because this concave side is now closer, its radius becomes radius 1, and the convex side's radius becomes radius 2. Does that make sense? Now, the 0.52 is not going to change. That stays the same. But now that R1 becomes a negative 25, the R2 becomes a D2. Just kidding. It becomes a negative 15. So I couldn't resist. The R2 becomes negative 15. And because we have negative, negative, the negative class, stay with me, gives us a positive. I was really hoping to get a couple more of these in, but oh well, we'll make it work. All right, so when we go through now, we're going to take the reciprocal of negative 25 and add the reciprocal of 15. So we take the reciprocal of negative 25 and add the reciprocal of 15, multiply by 0.52, which was the n minus 1, and then take the reciprocal. And what do we get this time? The exact same thing. You remember a moment ago I said if I take my glasses off and turn them backwards? For one thing, it's really weird. And because of the curving on the edges, It's blurry and weird, but right in the optical center, which is where my eyes are still looking, you still both look perfectly clear. I can still see you really well. Everything around you is weird and distorted in or something, but it's still clear because the lens still does the exact same thing no matter which side the object's on. So the nice thing about this is, although in a lot of the problems I'll say, assume this side is toward the object, it really doesn't matter. So long as you have the radii labeled correctly, you account for their signs correctly, and you plug it in correctly. Now, we were supposed to practice a lot more of this in class, and we did not have time to do so. So what I'm going to do, if I can find a pen, write this down. I'm going to have you still do the handout that's in the description of the video, but only do the first 2 problems. Only do the first 2 problems on the handout. Do not do all 4. Okay, we'll work on this more in our next lesson, and then we'll finish the handout that time. But I don't want you to do all 4 of them just because if you don't quite get it perfectly, I don't want you to do all 4 of them wrong. All right, you are dismissed. Have a wonderful rest of your day.